When we last had class a week ago, we had talked about the concept of impedance as being the ratio of the phasor voltage drop across an element or network's terminals divided by the phasor current flowing into the component or network's terminals. So today we are going to kick things off with the concept of admittance. So admittance is simply the reciprocal of impedance, and it therefore represents a ratio of the phasor current divided by the phasor voltage. Since this is a ratio of complex numbers, then Y, our admittance, must be a complex number itself. Expressed in polar form, it's going to look like this. So we have our phasor current, Im angle theta I, divided by our phasor voltage, Vm angle theta V. And so we will have a magnitude that is the ratio of Im over Vm and a phase angle of theta I minus theta V, which gives us the magnitude of our admittance, Y, absolute value of Y, with an angle theta Y. And we can see that theta Y is simply negative theta Z. So it is the opposite of the angle of the impedance, because the angle of the impedance, theta Z, was defined to be theta V minus theta I. So this is what our admittance looks like in polar form. In rectangular form, admittance is given by Y is equal to G plus JB, okay, where this G plus JB is identical to 1 over R plus JX. G is known as the conductance, and it represents the real part of the admittance. And B is known as the susceptance, and represents the imaginary part of admittance. Okay. You might also hear it as susceptibility, but it really means the same thing. Susceptance or susceptibility represents the imaginary part of the quantity admittance. Okay. Now, in DC circuits, our conductance G was simply the reciprocal of our resistance R. But because we have this complex relationship, that's no longer explicitly the case. So instead, we can find that G, our conductance, in terms of our impedance quantities, is given by resistance R divided by the sum of the resistance squared plus the reactance squared. And our susceptance B is given by a similar expression where it's negative reactance divided by the square of resistance added to the square of reactance. We can go the other way around. and find that resistance in terms of admittance quantities is conductance G over G squared plus B squared, and reactance X is negative B over G squared plus B squared. And I think actually there's an error here that I've made commonly among all of these things. And the reason why I say that is because the units don't make sense. Okay. Actually, now that I think about it, that's not entirely true. So let's look at this. Okay, so if we have resistance in the numerator, that has units of ohms. And then we have resistance squared plus resistance squared is just going to be ohms squared. So conductance will have units of ohms over ohms squared, which is 1 over ohms. Okay, so that does make sense. Sorry, I was thinking about I might need to have a square root here in the denominator of all of these things, which would effectively give me the magnitude of the impedance in the top quantities and the conductance in the bottom quantities, but dimensionally it doesn't look like that's necessary. So I apologize for even mentioning it because I may have confused you. So these do seem to be right as the units work out the way that I expect them to. Okay, so sorry about that. All right. The admittance of a resistor is simply 1 over the impedance of a resistor, or 1 over R, which could be written in rectangular form as 1 over R plus J0, or in polar form as 1 over R angle 0 degrees. From this, we can easily see that the units of admittance is the Siemens, much like that's the units of conductance in DC circuits. For an inductor has an impedance of j omega L, and so the admittance of an inductor must then be 1 over j omega L, which in rectangular form looks like 0 minus j times 1 over omega L, or in polar form looks like 1 over omega L with an angle of negative 90 degrees. And the admittance of a capacitor is the reciprocal of a capacitor impedance. So if the impedance of a capacitor is 1 over j omega c, the admittance of a capacitor is then simply j omega c. Or 0 plus j omega c in rectangular form, or omega c angle positive 90 degrees in polar form. Now, in this particular class, I tend to work almost exclusively in impedances. Okay. If I ever ask you to calculate the admittance, my expectation there would be for you to simply calculate the impedance and then take the reciprocal of it. Now, once we get into our electronics classes, where it's going to look like there are lots and lots of elements connected in parallel, we're going to start working with conductance quantities a lot more because the means by which to simplify them is easier. Conductances in parallel or admittances in parallel combine like resistors in series effectively. So anytime we see a combination of the sum of a bunch of conductances, we can simply treat that as, oh, it's these resistances in parallel. So Just to reiterate, in this class, much like in circuits 1, you've been introduced to this topic. Don't expect to get a whole heck of a lot of use out of it. Once you get into some of your higher level classes, specifically when you're dealing with concepts like network theory and things like that, conductances can begin to, or excuse me, admittances can begin to play a much bigger role. Okay? But for us, largely we'll just treat the admittance as the reciprocal of resistance and go on about our day. All righty, so we are now at a point where we can begin to do actual steady state sinusoidal circuit analysis, which is 100% a review of what we did in circuits 1. So my question to you guys is, how much time do you want to dedicate to reviewing these concepts of analyzing circuits in the frequency domain? I want to say that I've got something like 2 days set up on the syllabus. We could take those full 2 days, so that would be the remainder of this lecture and an entire extra class period on Friday. Or if you guys are comfortable with steady state sinusoidal analysis, we can really just kind of wrap that portion up today and move on to bigger and better things regarding steady state sinusoidal power and all that kind of good stuff. So what do you feel like? Do you feel like you need the review, or are you pretty comfortable? Yeah, so I effectively, I don't want to waste your time going over stuff that you already know. Sure, absolutely. That's generally what happens a lot for a lot of students. They get to this point in circuits 1 and then realize like, oh, they actually don't have to do super great on exam 3 in order to pass the class, and just kind of check out, which I can't really fault anybody on because the final exam is cumulative. I don't like it, but I keep being told to not change it. So we'll see how that goes in the future as I get more and more belligerent. But anyway, you guys had the advantage, in my opinion, of having a cumulative final where you didn't necessarily have to understand all of these concepts in order to get through that portion of the class, because so much of the material on your exam was old stuff. All right, so the very, very truncated version of steady state sinusoidal analysis is the reason why we are working all of our circuits in the frequency domain as opposed to the time domain is because it allows us to apply DC circuit analysis techniques using complex numbers to get the exact same result as a terrifying amount of calculus and trig identities would get us. Okay, so because it's allowing us to use DC circuit analysis techniques and to best utilize our time that we have for this review, what are the DC circuit analysis techniques that you feel the least comfortable with? So let me just rattle off DC circuit analysis techniques: Ohm's law, KCL, KVL, voltage division, current division, superposition, Thevenin and Norton equivalent circuits. Thevenin and Norton equivalent circuits, okay. Superposition, okay. All right, so let's do I've got a circuit here that I analyzed a couple of different ways, and I'm trying to think of, it's only got a single source, so I can't do superposition on it for sure, but I'm trying to think about if we could do Thevenin and Norton equivalent circuits in order to determine one of these quantities. The short answer is obviously yes, but is it actually going to be of any use? We'll find out. So, okay, so here's the circuit that we're going to look at first. So we have the following circuit where we have, and I'm just going to be strictly in the frequency domain here. So we have a 24 angle 60 degrees volts source connected to a 4 ohm resistor, which is in turn connected to a J6 ohm impedance inductor. We have a connection to an 8 ohm resistor, and then we have a minus J4 ohm capacitor over here. And our goal will be to determine this current, which I'm going to call IC phasor. Okay. And we are going to determine this quantity by finding the Thevenin equivalent of everything that's connected to that capacitor in order to simplify this circuit down into something that we can simply analyze. Okay. And in doing so, we will be reinforcing our Thevenin and Norton equivalent circuits. Bradley.
I wanted to ask if we were to approach it with mesh analysis. I know we're doing it for Thevenin.
We're not even going to bother with mesh analysis or anything like that yet. Let's focus on this particular analysis method, and then we'll open it up to other potential ways to solve it.
I was just going to ask if it would be possible.
Mesh is always possible. Nodal is always possible. It's depending on whether or not you have a computer that can solve it or not, because it's a system of complex numbers. There's no reason we can't apply literally any DC circuit analysis technique to this circuit. All of them are absolutely valid. KCL, KVL, if KCL and KVL are valid, then Ohm's law, or excuse me, then mesh analysis and nodal analysis have to be valid as well, because it's just multiple applications of those fundamental circuital laws. All right. Okay, so since we're finding the Thevenin equivalent circuit with respect to a particular element, in this case, our capacitor, which has an impedance of negative J4 ohms, what we have to do is disconnect that capacitor and then calculate the Thevenin voltage and the Thevenin resistance with that capacitor removed from the circuit. Because as you recall from circuits 1, or hopefully you recall from circuits 1, anytime we are taking the Thevenin equivalent with respect to a particular element, we have to remove that element from influencing the behavior of the rest of the circuit. So our Thevenin voltage, let's look at what chat says here. Complex power. We are absolutely going to talk about complex power, Drew, but we're going to get through simple analysis techniques before we get into our power relationships. All right, so with the capacitor removed, we have the following circuit: 24 angle 60 degrees volts connected to a 4 ohm resistor, a J6 ohm inductor, an 8 ohm resistor, and then our capacitor is removed, leaving behind a pair of terminals. And across this open circuit set of terminals will be our Thevenin voltage VTH phasor. So how might we go about determining that voltage VTH? That's absolutely correct. So the voltage drop over our J6 ohm inductor is the same as our Thevenin voltage, because no phasor current can flow through our 8 ohm resistor. because it's not part of a closed current carrying loop, which means no voltage drop occurs over it. So VTH is the exact same thing as the voltage drop over our inductor. So how do we determine the voltage drop over our inductor? If we all agree that that's what we should be doing. Voltage division, that is an absolutely wonderful way to do this because we can get the thing that we're looking for with a single equation. So applying voltage division, VTH here is going to be 24 angle 60 degrees volts multiplied by J, which that does not look like a pretty good J. So J 6 ohms over 4 plus J 6 ohms. And because we have complex numbers, there's no way I can do this in my head. So I'm going to throw it into my calculator, 24 angle 60 times 6i over 4 plus 6i. And I get 19.969 angle 93.690 degrees. Okay. So now we would need to find the Thevenin equivalent impedance in this case. So please recall that anytime we're trying to find the Thevenin equivalent impedance, we need to be looking at a dead network, which means we're going to have this same exact circuit. We're going to be looking in through these open circuit terminals where the capacitor was, but our phasor voltage source will now be off. How do I turn off a voltage source? Short circuit, absolutely right. So I will have a short circuit here, a 4 ohm resistor here, my J6 ohms inductor. Here I have my 8 ohm resistor, open circuit where my capacitor was, and my Thevenin equivalent impedance, Z Thevenin, to me, looks like 8 ohms in series with the parallel combination of J6 and 4. Does anybody see anything different than that? So my inductor and my 4 ohm resistor are in parallel because they share this top middle node and this bottom kind of outside node. And then I have an 8 ohm resistor in series with that. So that's going to look like 8 ohms plus, let's see, 6 times 4. So that's J 24 ohms squared over 4 plus J6 ohms. I get an impedance of 10.926 angle 9.727 degrees ohms, or 10.769 plus J 1.846 ohms. Typically speaking, I prefer to use polar form for voltages and currents. And then for impedance, it's just kind of whatever I feel like. So that's why I'm giving you both options here. I largely stick to polar form for pretty much everything, but there are definitely times where I'm looking at the rectangular form of an impedance because that sometimes gives me information that I'm interested in. Not really so much here, although if we wanted to figure out what the time domain equivalent circuit was, we would need to be looking at the rectangular form of that. So for instance, if I wanted to know what actual component values would give me this, it would be our voltage source in series with a 10.769 ohm resistor in series with an inductor that has an impedance of 1.846 ohms at whatever frequency we're working at. So this rectangular form is absolutely necessary to work backwards to figure out what this looks like in the time domain. Not particularly relevant to this circuit, but it's absolutely something I ask you to do in the homework set that will be assigned today. Connor.
I apologize for probably making you repeat yourself. I'm just incredible. So whenever you do the Thevenin impedance, you're just turning off all sources.
Yes. So actually, that's not entirely true. All independent sources. Yes. So all independent phasor voltage sources and all independent phasor current sources. Any dependent sources would still have to be left in the circuit, and we would be required to use a test source method in order to determine the equivalent impedance directly.
What about DC independent sources?
DC independent sources would also be turned off. That's opening up a little bit of bag of cats here that we're not quite ready for yet. We are absolutely going to talk about that. So that's one topic that was not covered, and this is a tangent. That's okay. I take lots of them. That's one concept that was not covered in circuits one is the concept of multi-frequency circuits. And that's something that we will talk about in this class. And actually, I'll probably talk about multi-frequency circuits as an excuse to use superposition in just a couple of moments. Okay? But if we had a DC source in there and an AC source, all of our inductors and capacitors are going to have a different impedance depending on which source is acting on them. And so what I mean by that is we know that in a DC circuit, a capacitor looks like an open circuit, so it has an infinitely large impedance, whereas to an AC excitation signal, it has a frequency dependent impedance. Those match up, right? So let's finish this problem and then we'll talk about that in a moment as a lead into multi-frequency circuits. Okay, so we have a Thevenin equivalent voltage and we have a Thevenin equivalent impedance. Our ultimate goal, if you recall, was to determine this quantity IC. So you may be asking yourself, well, how the hell did all that work we just did make that any easier to solve? Well, we can simplify our original circuit to V Thevenin in series with Z Thevenin, and then connect that equivalent circuit to our capacitor, which had an impedance of negative J4 ohms. And now determine the quantity IC as simply IC is equal to the V Thevenin we determined earlier divided by Z Thevenin minus J4 ohms. So using stored variables in my calculator, I get a current of 1.818 angle 105 degrees amps current flowing through my capacitor, using the Thevenin equivalent here to make determining the quantity of interest fairly trivial. Okay. Now, before we explore what I was talking about with Connor and the concept of frequency dependent impedance and how to take that into account, let's scroll back up here and talk about other ways that we could have solved the circuit. Okay. So, as Bradley originally questioned, we could, if we were so inclined, perform mesh analysis on this circuit to determine that capacitor current IC. The reason why I tend to stay away from mesh analysis explicitly here is because I'm going to have a system of equations that I will have to solve that includes complex numbers. And the only way to do that is either to use a concept called Cramer's rule, which isn't particularly difficult, but it's very tedious in order to solve that system by hand, or we would have to employ the use of a computer algebra tool like MathCAD or Wolfram Alpha to do it for us. And on our exams, we definitely do not have access to, or at least the in-class portion of our exams, we do not have access to computer algebra solvers. Okay. One thing that we could potentially do here would be to apply nodal analysis. You may be asking yourself, well, why can you apply nodal analysis, which is setting up a system of equations, and not mesh analysis? And the short answer here is that the nodal analysis isn't really nodal analysis. It's more applying Kirchhoff's current law at our top middle node. And so what I mean by that is, not going to go through this in full detail, because if you want to see this particular approach in practice, you can look at any of my Engineering 221 videos, because this is what I wind up doing 70+% of the time. If I treat this bottom node as ground and combine these two, the 8 ohm resistor and the negative J4 ohm capacitance, into a single equivalent impedance of just 8 minus J4, if I apply Kirchhoff's current law at this top middle node, the only unknown voltage is the voltage at this top middle node. Dividing that voltage by this 8 minus J4 ohm impedance gives me my capacitor current. So it's really just application of KCL and then Ohm's law, but it looks awfully like nodal analysis. Another analysis technique that could be used here would be a source transformation. So we have a practical phasor voltage source because we have a 24 angle 60 degrees volt source in series with a 4 ohm resistor, which could be converted into a practical phasor current source. From that point, we would have a current source in parallel with a 4 ohm resistor, in parallel with a J6 ohm inductor, in parallel with an 8 minus J4 ohm impedance. And then current division would get us our answer in a single step after that transformation. We could always suffer through finding the equivalent impedance of everything that's connected to the source, and then using Ohm's law to find the current that flows through the 4 ohm resistor, and then apply KCL and KVL to kind of back calculate every current and voltage in the circuit as well. But I would argue that's the least practical way to do it, although it absolutely works because it just relies fundamentally on KCL, KVL, and Ohm's law. It takes the most amount of time because we have to shrink everything down into 2 elements and then expand it back out to figure what we're looking for. So as an absolute last resort, that's fair game, but practically speaking, it's the longest possible method to solve this circuit. So this simple circuit here, I think I've discussed, what, 5, 6 different ways we could approach getting this quantity using really every conceivable DC circuit analysis technique I can think of other than superposition, which we can't use because there's only a single source, right? So we used Thevenin equivalent circuits, which in turn refreshed our knowledge of voltage division here in this first step, impedance combination in the second step, and then using Ohm's law to wrap things up at the end. We talked about how we could use source transformations and current division, nodal analysis, mesh analysis, KCL, KVL, Ohm's law from the jump. There's really any way that you can think of can be applied to any of these circuits. Okay, so whatever you are most comfortable with is the way that you should approach these. It's okay if it's nodal analysis and mesh analysis and things like that with regards to your homeworks on a test. That's going to bite you, or excuse me, on the in-class portion of the exam, that's going to bite you in the butt because you have to be able to solve that system by hand, which is absolutely doable, but is, in my opinion, an extraordinarily tedious thing to do. I used to make my circuits one students do it the first quarter I taught that class, and then I thought they were going to murder me in the parking lot, and so I stopped making them do it. So anyway, it's no fun to take a problem effectively as, you know, this difficulty, ask them to do nodal and mesh, and then make them waste 45 minutes of doing complex algebra, moving stuff around in order to make it work. Anyway, all right, so how do you, whoever asked, John, was it you with Thevenin and Norton? Did this help at all? Okay. If we did a Norton equivalent circuit representation of this, it would actually come out to be literally the exact same thing as if we had done a source transformation. So that's why I didn't particularly go through that one. But the only difference with the Norton equivalent circuit would be that we would short circuit this guy here and then find the current flowing through it, which we would most easily do using a source transformation. So, all right, so combining Connor's comment regarding what would happen if a DC source were in here, and me expanding on that to the topic of multi-frequency circuits, and Skylar's desire to see us apply the principles of superposition to analyze a circuit, I am now going to formally introduce multi-frequency circuits. So let's say that I have the following circuit. This one's going to be fairly straightforward. I have a voltage source, let's call it VS1 of T, that I will have to identify momentarily. I have a 5 ohm resistor, a 2 Henry inductor, and then a 1/2 farad capacitor. And then on this side, we'll have another voltage source. Let's call it VS2 of T. I'm going to define what those voltage source values are in a moment. But let's say that I'm interested explicitly in this quantity, ZL, as a function of time. So this is a time domain circuit. We are interested in a time domain quantity. VS1 and VS2 are going to be sinusoidal excitation sources so that we can work all of our analysis in the frequency domain. But the hiccup here, the thing that's going to make it arguably difficult, is that VS1 of T will be 10 cosine 2T volts, and VS2 of T will be 8 cosine T volts. So that we have, goodness, excuse me, different angular frequencies to consider. Okay. So I'm not using explicitly a DC source as Connor had suggested, but the same thought process will apply. Okay. So the problem with this circuit, as I was mentioning a few moments ago, is that all of our capacitors and all of our inductors will experience two different impedances, or will exhibit two different impedances depending on which of the sources that we're applying, right? So we can't look at this circuit all in one go because we wouldn't know whether to treat the inductor as a, let's see, so 2 times 2, so a J4 ohm impedance or a J2 ohm impedance, right? Because it actually exhibits both of them simultaneously. Similarly, our capacitor is going to exhibit a negative J impedance and a negative 1/2 J, excuse me, negative 2J impedance, depending on which frequency we're looking at. The only way for us to analyze this circuit is to use a superposition technique where we're analyzing the circuit at a single frequency at a time. Okay. If there were multiple sources operating at the same frequency, we could double superposition it, I guess you could say, by analyzing it with a single source on at a time, but it's going to limit what we can combine and what we can't combine. Okay. So with voltage source 1 on, and voltage source 2 off, our frequency domain equivalent circuit is going to look like this, right? So what's the phasor equivalent of VS1? Not intended to be a trick question. What's that? Yeah, 10 angle 0. Absolutely right. Our 5 ohm resistor is going to look like a 5 ohm resistor regardless of what frequency we're operating at. What kind of impedance will our inductor have? J4 ohms, absolutely right. So that's simply taking J times omega, which in this case is 2 radians per second, times L, which is 2 henries. So that's giving us an impedance of J4 ohms. What about our capacitor? Negative J, right? Yeah. So negative J 1 ohms. And then our voltage source VS2 will simply be off. So we replace it with a short circuit. And our goal here is to determine phasor voltage VL prime, like so. So how would we go about doing that? Just voltage division the one time. Yeah. So our inductor and our capacitor are in parallel, so we can just do voltage division where we're finding the voltage drop over that parallel combination, right? So that would mean VL prime in this case would be 10 angle 0 degrees volts multiplied by, so let's see what we're going to have here. J4 ohms times minus J1 ohms over J3 ohms That's J4 minus J1. So let me throw this in a calculator. So that's going to be 10 angle 0 4i times minus 1i over 3i. I get 13.333 angle negative 90 degrees. Connor. Wonderful thing. Yes, absolutely. I absolutely forgot something there. So thank you. Yes. So in my denominator, I absolutely should have 5 pluses. So actually, I made lots of mistakes here. Yeah. Yeah. All of that is over. So yeah, thank you. I just completely biffed this. Thank you. All right. So let's get this going correctly here. So the impedance of the capacitor is 1 over J times omega, which is 2, times C, which is 1/2. So that's literally 1 over J1, which is the exact same thing as negative J.
That C isn't in it, okay. I'm just used to seeing.
Yeah. All right, so applying voltage division correctly, thank you for pointing that out. Just total brain fart there. In our numerator, we would have that equivalent impedance, which is what I had it written down originally. J4 ohms times minus J ohms over J3 ohms. And our denominator should be 5 ohms plus what we have in the numerator. So that's going to be J4 times minus J1 over J3. And let's do this correctly. I get 2.577 angle negative 75.068 degrees. Again, thank you very much for catching the egregious mistake that I made. All right. Now we would analyze the circuit with VS1 off and VS2 on. And so what that's going to look like is we have our VS1 voltage source shorted out, our 5 ohm resistor still looks like a 5 ohm resistor. Our inductor will now look like a J2 ohm impedance. Our capacitor will look like a negative J2 ohm impedance if I'm doing my mental math correctly. So it's going to be the reciprocal of 1/2, which is 2 times negative J. And then over here, we have an 8 angle 0 degrees voltage source. And we are now trying to find this quantity VL double prime. Connor.
denominator of the last equation you just crunched, the second portion that passes the denominator as well, that is J3 omega.
J3 ohms.
Ohms.
Yes.
I mean, ohms, that's what I meant.
Yeah. I mean, that is a capital omega, yes. Specifically, I'm trying to say J3, which is simply J4 minus J1. All right, so how would we analyze this one? Also voltage division, effectively the exact same one, right? Let's see if I can do it this time without making a terrible mistake. So VL double prime would be 8 angle 0 degrees volts. I'm going to have 5 ohms times J2 ohms over 5 plus J2 ohms divided by minus J2 plus what I have in my numerator. And so let me throw this into the calculator. I get 20 angle 90 degrees volts. Let me double check that real quick. Okay, there we go. So 8 times 10i over 5 plus 2i divided by minus 2i plus 5 times 2, so that's 10i over 5 plus 2i. Yep, 20 angle 90 degrees. Okay. All right. So what do we do now? I'm using a single prime designation for the first time we do superposition, double prime designation for the second time we apply superposition. If we had 3 sources, I would have a triple prime designation. That's just my way of designating the different iterations of superposition that we're doing. So it has nothing to do with the time derivative or anything like that.
Helps to plot the numbers.
Yes.
Yeah.
Okay. So what should we do here?
Add them together.
No. So let's talk about why we can't just add them together, because that's what our instinct would be using superposition. But the fact that these analyses occurred at 2 different frequencies is why we cannot simply add them together, right? This analysis occurred at an angular frequency of 2 radians per second. This analysis occurred at an angular frequency of 1 radian per second. So this is where phasors get a little bit wonky, right? Because they represent the magnitude and phase angle of a signal, but they do not have any built-in reflection of what the frequency of oscillation actually is. That's exactly what we have to do. We cannot add the phasors together. We can only add the time domain representations together. You're 100% correct there. So VL of t would be 2.577 cosine 2t minus 75.068 degrees plus 20 cosine t plus 90 degrees volts. It cannot be simplified further than this. So if we are taking the voltage drop over any of our elements here and we are experiencing oscillations at two different frequencies, we should expect two different terms in our result, one for each of the frequencies of oscillation. Okay, so you're 100% right. When we have a multi-frequency circuit, we can do all of our analysis in the frequency domain, but we have to break it down into an analysis at each excitation frequency, convert our results back into the time domain, and then add them together. We cannot add them together in the frequency domain and convert to time. We will get an erroneous result. John.
Oh, I'm just curious about this. That second term, you change that to sine.
So T plus, yeah, so we could, if we felt so inclined, there's nothing wrong with that whatsoever. But I'm just in the habit of expressing everything as a cosine because that's how we get to the frequency domain. So there wouldn't be an issue whatsoever with calling that 20, let's see, so if we subtract 90 degrees to go from sine to cosine, we'd add 90 degrees to go from cosine to sine. So this would actually more likely be negative 20 sine t to get rid of the phase angle. But at this point, it's 6 of one, half a dozen of the other. They literally represent the same thing. So I've introduced a new concept, which will absolutely be in your homework, while also hopefully reinforcing or at least re-explaining how to apply the superposition principle to analyzing circuits. Skylar, do you feel okay with this? All right, so we have less than 15 minutes left of class. So we've spent an hour analyzing two circuits. So I feel like introducing another one right now, we're not going to get through it. So I'm going to repeat my question from previously. What do you guys want to do next? Do we want to spend another day looking at frequency domain circuit analysis techniques, or do we want to move along to our power relationships? Yeah, yep. All of the analysis is the same. So yes, so you're 100% correct. We're going to wind up getting some review in the power bit as well anyway. So that's correct. We are going to recover instantaneous power and average power as we did in circuits 1. We are going to supplement that with what's called the maximum average power transfer theorem. So that's going to be something new. Then we are going to get into our complex power relationship. So actually, I take that back. We're going to introduce the concept of effective values again. Then get into our complex power relationships. Complex power, apparent power, average power, reactive power, power factor, all that kind of good stuff. We are going to talk about power factor correction again. And we're going to spend as much time in this class talking about those concepts as we did in circuits 1. Because those are our fundamental building block or jumping off point to get to the fourth topic in this class, which is the concept of three-phase power. What we are going to do slightly before we get into three-phase power is introduce the concept of filters. Filters are all about kind of what we did here, recognizing that the impedance of capacitors and inductors change as a function of frequency and exploiting those relationships to either pass or attenuate specific portions of signals. So once we wrap up this steady state sinusoidal portion of the class, we're going to take a couple of days to talk about filters before we jump into our three-phase relationships, which is the last set of topics for the class. So that's where things are headed. Elijah. So it depends, right? So if it's all, are you talking about filters specifically and how? Yeah. So what we have here in both instances is a simple voltage divider circuit, right? Here we're combining these two impedances together, and it gets really small when we combine them together, which is why we see that the voltage gets attenuated. Here, when we combine those impedances together, its magnitude is actually larger than either of the constituent parts, which is why our voltage drop gets larger. And it is absolutely due in some part to the frequency dependence of the impedance of the inductor and capacitor. The frequency dependence of the impedance of the inductor and capacitor. Yes. The concept of filters explores that by saying, well, what if we weren't working at a single specific frequency? What if we were sweeping across all possible frequencies? How would this circuit behave? Yes, we're gonna, it's not gonna be super bad. In circuit 3, we're gonna get real detailed using what they're called Bode plots and phase response plots and all that kind of stuff. In this class, we're really only gonna be concerned about what the magnitude response looks like. But yeah, you can get really, really granular in your detail and identify what are called poles and zeros and get like all kinds of neat transfer functions and all that kind of good stuff with filters. We're not going to do that deep of a dive just yet, where I'm just going to dip our toes in so that when you have a lab on it in the fall, you're not completely and utterly lost. All right, so I believe what the consensus feels like is we're going to move along to power and then reinforce things as we go. Does anybody have any opposition to that? Move on. When will you start working on your design projects? Okay, so design project number 1 has been posted. It's on Moodle and all that kind of stuff. It's due at the end of the quarter. Your next design project will be covering filter circuits, so I can't post that one until we cover them. So look for that probably at the end of next weekish, I believe would be a reasonable time to put that up. Did that answer your question, Drew? All righty. Okay. Well, that is enough out of me for today. I hope you all had a wonderful Easter break and are transitioning back to having to do work and all that kind of stuff better than I am. So I'll see you guys on Friday. We'll talk about, start talking about our power relationships.